This is a video on the acid-base properties of salts. As you can see, there's a heading here that says neutral solutions. So what it's trying to indicate is that some salts, when they're dissolved in water, form a solution which is neutral and should have a pH of about 7 at a temperature of 25 degrees Celsius. Other salts, when you dissolve them in water, will either make the solution acidic or basic. So sometimes we might actually ourselves take a salt and dissolve it in water. Other times what we have to worry about is that the salt, or a salt, is the product of an acid-base neutralization reaction. So when we add an acid to a base, or a base to an acid, they neutralize each other, but in the process they produce a salt. Sometimes the salt, depending upon the type of salt, could be neutral. Other salts are either acidic or basic, and we have to consider that when we are looking at the process of a titration, in which you're neutralizing an acid with a base or a base with an acid. Neutral solutions. When you have a salt that contains either an alkali metal or an alkali earth metal, with the exception of the Be2+ ion, and the conjugate base, the conjugate base of a strong acid, for example, like Cl-, which comes from HCl, and Br-, which comes from HBr, and NO3-, which comes from HNO3, that salt would be neutral. For example, NaCl. NaCl, sodium chloride, dissolves in water, breaks apart into Na ions and Cl- ions. This salt is considered to be neutral. The Na+ ion is an alkali metal. It comes from group 1A, and therefore has no acidic characteristics. The Cl- is the conjugate base of a strong acid, HCl. And we know that the conjugate base of a strong acid has 0 base characteristics. So this is a group 1 metal, and this is the conjugate base of a strong acid, and this has 0 acid characteristic, this has 0 base characteristic, and therefore this solution, for all intents and purposes, is neutral. And if you haven't figured it out, it's the cation that can make the solution acidic, and it's the anion that can make the solution basic. It's the cation which comes from a base, and the anion which comes from the acid. Basic solutions. Salts derive from a strong base and a weak acid, such as CH3COONA. When this salt, CH3COONA, is dissolved in water, or is produced, let's say, from an acid-base neutralization reaction, this solution should be basic. The Na, our cation, we have to check and see if it has any acidic characteristics. Well, it's an alkali metal, which means it's a group 1 metal, therefore we can consider it to have 0 acid characteristics. Let's take a look at our anion here. Our CH3COO negative, this comes from the weak acid, acetic acid, which is CH3COOH. Since it comes from CH3COOH, a weak acid, this is its conjugate base. And we know that the conjugate base of a weak acid has significant base characteristics, strong enough that we have to consider it as acting basic. So when this substance is formed in solution from the acid-base titration, this is not going to have any effect on the pH, but this will, because it's the conjugate base of the weak acid. And so it will hydrolyze and react with water to form the acetic acid and the hydroxide ion. So this solution is going to be basic. Acidic solutions. Salts derived from a strong base and a weak acid, like NH4Cl. NH4Cl, when it is produced from the titration of NH3 and Cl, or HCl, excuse me, a titration between NH3 and HCl, we get NH4+ and Cl-. So when the titration occurs and the NH4Cl is produced in solution, that's going to dissolve, right, or stay dissolved. We know that the Cl- comes from the strong acid and therefore has no real base characteristics. But the NH4+, which comes from our weak base, is going to act like a weak acid. So remember, the cation has, we have to check the cation for acid characteristics, we have to check the anion for base characteristic. This comes from the strong acid and therefore has 0 base characteristics, but this comes from a weak base, which means it itself is a weak acid, and therefore will have measurable acid characteristics. So we see that it's going to hydrolyze in water, produce NH3 and H+. Salts with small highly charged metal cations like aluminum 3+, Cr3+, and Be2+ will also be acidic in solution. They form complex ions with water molecules which can undergo hydrolysis. So this aluminum here will actually form a complex ion with 6 water molecules to make the aluminum hexa-aquo 3+ ion, which itself can react in water, will hydrolyze in water, and lose a proton. So here's the aluminum, and here are the 6 water molecules which are covalently bonded to the aluminum. That means that the oxygen on the water molecule donates both of the electrons to the covalent bond instead of 1 electron from the aluminum and 1 from the water. And the aluminum uses its d orbitals to accept those electrons. And here, this hydrogen is undergoing hydrolysis. It's being pulled away by this water molecule, forming the hydronium ion. And the ion, which now is AlOH H2O5, with a 2+ charge instead of a 3+ charge, because we lost the positive charge, so that means it reveals an extra negative charge. Solutions in which both the cation and the anion hydrolyze. Well, if the Kb for the anion is greater than the Ka, then the solution is basic. If the Kb for the anion is greater than the Ka, or less than the Ka for the cation, then the solution is acidic. And if the Kb and the Ka are about the same, then the solution is about neutral. And of course, the below is a list of, or a summation, and some examples of all the things that we just discussed. So take your time, stop right there, take a good look at it, and we'll see you in class tomorrow. Have a good night.